Our sun is enormous. 1 million Earths could fit inside it. Its surface burns at 5,500 degrees Celsius. Every second, it converts 600 million tons of hydrogen into pure energy. To us, it's the definition of power. But here's what nobody tells you. Our sun is average, ordinary, unremarkable. In the cosmic zoo of stars, our sun is a house cat. And there are lions out there that would make it look like a speck of dust. Stars so massive, they shouldn't exist. Stars so heavy, they bend the laws of physics. Stars so powerful, they burn through their entire fuel supply in a cosmic heartbeat. And somewhere in this universe, one star holds the title. The most massive star ever discovered. But how massive can a star actually get? Is there a limit? And what happens when a star pushes past that limit? Let's find out. To understand truly massive stars, we first need to understand what makes a star heavy in the first place. Mass and size are not the same thing. This is where most people get confused. A star can be enormous in size, but relatively light in mass. It's like a giant balloon. Huge volume, not much weight. Or a star can be compact in size, but incredibly dense. Like a cannonball. Small volume. Tremendous weight. The most massive stars are not necessarily the largest stars. And the largest stars are not necessarily the most massive. Our sun has a mass of 1 solar mass. Obviously, that's the baseline. Everything else gets compared to it. Sirius A, the brightest star in our night sky, is about 2 solar masses. Double our sun. Impressive, but nothing special. Let's climb higher. Bellatrix, the left shoulder of Orion, is 8.6 times more massive than our sun. Its core is crushed under so much pressure that fusion reactions run wild. It burns hot, it burns fast, it burns blue, but there's a price. While our sun will live for 10 billion years, Bellatrix has maybe 7 million years left. It's burning through its fuel at an insane rate. This is the trade-off. The more massive the star, the shorter its life.
Ow.
But even Bellatrix is nothing compared to what comes next.
Ow.
Let's talk about a true monster, R136A1. This star sits in the Tarantula Nebula about 160,000 light-years away, and it breaks the rules. Scientists used to believe that stars couldn't grow beyond 150 solar masses. The physics didn't allow it. Beyond that limit, a star would become so unstable, it would tear itself apart. R136A1 laughs at that limit. It's estimated to be 265 times more massive than our sun. Let that sink in. 265 suns crushed into a single star. How does it exist? The leading theory is collision. 2 already massive stars smashed into each other and merged.
Ouch.
The result was something that shouldn't be possible through normal star formation, a true cosmic accident. But mass is just one part of the story. What does 265 solar masses actually mean? It means R136A. One produces energy at a rate we can barely calculate. In just 4 seconds, it releases as much energy as our sun produces in an entire year. Its surface temperature exceeds 50,000 degrees. It's almost 10 times hotter than our sun. And most of its radiation isn't even visible light. It's ultraviolet, deadly, invisible. If you could somehow stand near R136A1, you'd be vaporized before your eyes could even register the light. But here's the tragic part. R136A1 is dying. It's only about 1 million years old. It probably has less than another million years left. Compare that to our sun's 10 billion year lifespan. R136A1 lives fast and dies young. Cosmic rock star burning out before its time. And it will die in the most violent way possible. When R136A1 finally exhausts its fuel, it won't fade quietly. It will explode in what's called a hypernova. An explosion so powerful it will briefly outshine entire galaxies. The shockwave will sterilize everything within hundreds of light years, and at its core, something even stranger will form. A black hole. Some scientists believe R136A1 might even trigger something called apparent stability supernova. This is when the star's core becomes so hot that energy converts directly into matter and antimatter particles. The result is total annihilation. No black hole, no neutron star, nothing left behind. The star completely destroys itself, erased from existence. But wait, is R136A1 actually the most massive star in the universe? Here's where it gets complicated. R136A1 is the most massive star we've confirmed, but there are candidates that might be heavier. The problem is measurement. These stars are incredibly far away. They're often surrounded by gas and dust that obscures our view. They're so bright that their light saturates our instruments. Calculating their exact mass requires complex models. Those models have uncertainties. Some astronomers believe there could be stars exceeding 300 solar masses, maybe even more. We just haven't confirmed them yet. But there's a hard limit. At some point, mass becomes the enemy of existence. Beyond roughly 150 to 300 solar masses, stars face what's called the Eddington Limit. Here's how it works. A star's gravity pulls everything inward. That's what holds it together. But radiation pressure pushes outward. Light itself exerts force. In extremely massive stars, radiation pressure becomes so intense that it starts pushing the star's outer layers away. The star literally blows itself apart from the inside. This creates a ceiling, maximum mass that stars cannot exceed, unless they cheat. Collision is one way to cheat. Two stars merge faster than radiation can tear them apart. Another possibility is rapid accretion. Star devours material so quickly that it gains mass before it can destabilize. But these scenarios are rare, extremely rare. Most stars never come close to these limits, which makes R136A1 even more remarkable. It exists at the edge of possibility, a freak of nature, statistical anomaly. And yet, there it is, burning defiantly in the Tarantula Nebula. So where does this leave us? We found stars that push every limit we thought existed. R136A1 at 265 solar masses. Possibly more massive stars waiting to be confirmed. And the theoretical maximum is somewhere around 300 solar masses. But here's what fascinates me most. Even the most massive stars are temporary. 136A1 will be gone in 1,000,000 years, a blink of cosmic time. Our sun will outlive it by 9 billion years. The universe doesn't reward excess. It rewards balance. The biggest stars burn brightest, but disappear fastest. The modest stars like our sun burn steadily and endure. Maybe there's a lesson there. Or maybe it's just physics. Either way, when you look up at the night sky tonight, remember this. Every star you see is a nuclear furnace. Every point of light is a story of gravity and fusion and time. Some of those stars are small and red and will burn for trillions of years. Some are massive beyond imagination and have already begun their death spiral. And somewhere out there, 160,000 light years away, R136A1 is blazing with the light of 8 million suns, the most massive star we know. For now, because the universe is vast, our telescopes are limited, and there's always something bigger waiting to be discovered. Is R136A1 the most massive star in the universe? Probably not, but it's the most massive one we've found. And that's what makes astronomy so exciting, not the answers we have, but the questions we're still asking.